For purely resistive or direct current loads, power calculations can be quite straightforward. The key concept to understand is that for a purely resistive load, the power available for a given load remains consistent whether you are using single-phase or three-phase, provided the voltage is the same. Let's break down why the initial statements are incorrect and delve into the underlying principles. The first incorrect statement suggests that when using three-phase power versus single-phase, the available power for a given three-phase load would have to be increased by 73.2% for the same load at single-phase. This is not accurate. The power delivered to a purely resistive load depends on the voltage and the current flowing through it. The formula that governs this relationship is power equals voltage times current, often written as P equals V times I. If the voltage remains constant and the load's resistance is fixed, the current will also remain constant, and therefore the power will be the same irrespective of whether it's single-phase or three-phase. Now, you might be thinking about the differences in voltage between single-phase and three-phase systems. For example, you might have a single-phase 240 volt system and a three-phase 208 volts or 480 volt system. However, when comparing the power delivered to a specific load, you would need to ensure that the voltage applied to that load is the same in both the single-phase and three-phase scenarios. If the voltage is the same, the power delivered to the resistive load will also be the same. The second incorrect statement asserts that a given load, whether resistive or direct current, uses only 57.7% of the power it uses at single-phase compared to three-phase. Again, this is not true if the voltage is the same. The power consumption of a resistive or direct current load is determined by the voltage applied across it and its resistance or impedance. As mentioned earlier, power equals voltage times current. If the voltage and resistance remain constant, the power remains the same, regardless of the phase configuration. The third incorrect statement is just another variation of the previous two, emphasizing the misunderstanding of power delivery in resistive and direct current loads. The calculation presented, which results in a reduced current value, is not valid when comparing single-phase and three-phase systems powering the same resistive load at the same voltage. To further clarify, let's consider a scenario with a 10 kV amps load at 240 volts in both single-phase and three-phase configurations. In a single-phase system, the current can be calculated by dividing the power in volt-amps by the voltage. So, 10,000 volt-amps divided by 240 volts equals approximately 41.66 amps. Now, it's important to understand that this calculation gives you the current in one leg of the single-phase circuit. For a three-phase system, the calculation is a bit different because the power is distributed across three phases. The formula for three-phase power is power equals the square root of 3 multiplied by the voltage, multiplied by the current, and multiplied by the power factor. For a resistive load, the power factor is 1. If we rearrange this formula to solve for current, we get current equals power divided by the square root of 3 multiplied by the voltage. Now, if we assume that the 10 kV amps load is the total three-phase power and the line-to-line voltage is still 240 volts, the calculation would be 10,000 volt-amps divided by the square root of 3, which is approximately 1.732, multiplied by 240 volts. This gives us a current of approximately 24.5 amps per phase. However, it is crucial to note that the 240 volts in the three-phase calculation is assumed to be the line-to-line voltage. If the load is connected in a delta configuration to a 240 volts three-phase system, then this calculation is valid. However, if the load is connected in a Y configuration, the voltage across each phase would be 240 volts divided by the square root of 3, which is approximately 138.56 volts. In that case, the current calculation would need to be adjusted accordingly. In summary, the key takeaway is that for a purely resistive load, the power it consumes depends on the voltage across it and its resistance. If the voltage and resistance are the same, the power consumption will be the same regardless of whether it's single-phase or three-phase. The incorrect statements likely arise from confusion about how three-phase power is calculated and distributed, particularly when dealing with different voltage configurations and load connections. To avoid these misunderstandings, always ensure you are using the correct formulas and voltage values for your specific circuit configuration. Remember that single-phase power is calculated as power equals voltage times current, while three-phase power is calculated as power equals the square root of 3 times the voltage times the current times the power factor. Also, be mindful of whether you are using line-to-line voltage or line-to-neutral voltage in your calculations, especially in Y-connected systems. Now let's delve a bit deeper into the practical applications of these principles. In residential settings, you typically encounter single-phase power, commonly at 120 volts or 240 volts. Appliances like lights, televisions, and small kitchen appliances are usually powered by 120-volt circuits, while larger appliances like ovens, dryers, and air conditioners often use 240-volt circuits. In commercial and industrial settings, three-phase power is more prevalent, especially for powering large motors, industrial equipment, and high-capacity heating systems. Three-phase power offers several advantages over single-phase power, including higher power capacity, smoother motor operation, and better efficiency. However, for purely resistive loads like electric heaters or incandescent lighting, the power consumption principles remain the same, regardless of whether they are connected to a single-phase or three-phase system, assuming the voltage is the same. Let's consider a practical example. Suppose you have an electric heater with a resistance of 10 ohms. If you connect it to a 120-volt single-phase circuit, the current flowing through it will be voltage divided by resistance, which is 120 volts divided by 10 ohms, equaling 12 amps. The power consumed by the heater will be voltage times current, which is 120 volts times 12 amps, equaling 1440 watts. Now, if you were to connect the same 10 ohms heater to a three-phase system with a line-to-neutral voltage of 120 volts, the current and power consumption would remain the same. The only difference is that in the three-phase system, you could potentially connect 3 of these heaters, 1 to each phase, and draw 3 times the power from the system. However, the power consumed by each individual heater would still be 1440 watts. It is also important to understand the concept of power factor. Power factor is a measure of how effectively electrical power is being used. For purely resistive loads, the power factor is 1, which means that all the electrical power being supplied is being used to do work. However, for inductive loads like motors and transformers, a power factor is less than 1, which means that some of the electrical power is being used to create a magnetic field and is not being used to do work. This reactive power can cause inefficiencies in the electrical system, and it is often necessary to correct the power factor by adding capacitors to the circuit. In summary, when dealing with purely resistive or direct current loads, remember that the power consumed depends primarily on the voltage and resistance. The phase configuration, whether single-phase or three-phase, does not affect the power consumption as long as the voltage remains the same. Always use the correct formulas for calculating power in single-phase and three-phase systems, and be mindful of the voltage values and load connections. Understanding these principles will help you avoid common misconceptions and ensure that you are using electrical power efficiently and safely. Let's expand on some additional nuances that are critical to grasp when working with single-phase and three-phase systems, particularly when dealing with resistive loads. One area of potential confusion lies in the different voltage configurations within three-phase systems. As previously mentioned, you can have a three-phase system with a line-to-line voltage of 240 volts, 480 volts, or even higher. However, the voltage to ground or line-to-neutral voltage will be different depending on whether the system is Y-connected or delta-connected. In a Y-connected system, the line-to-neutral voltage is equal to the line-to-line voltage divided by the square root of 3. For example, in a 480 volts Y-connected system, the line-to-neutral voltage would be approximately 277 volts. This means that you can connect 277 volts rated resistive loads directly to the line-to-neutral voltage in a 480 volts Y system. On the other hand, in a delta-connected system, the line-to-line voltage is equal to the phase voltage, and there is no neutral connection. This means that you cannot directly connect a 277 volts rated load to a 480 volts delta system. Instead, you would need to use a transformer to step down the voltage to a suitable level. Another important consideration is the ampacity of conductors. The National Electrical Code, or NEC, provides guidelines for determining the appropriate size of conductors for different types of loads. For example, NEC Table 310.15b16 lists the allowable ampacities of insulated conductors rated up to 600 volts, based on their insulation type and ambient temperature. When sizing conductors for resistive loads, you need to ensure that the conductor ampacity is sufficient to carry the full load current, plus any applicable directing factors for ambient temperature, number of conductors in a raceway, or other conditions. For example, if you have a 20 amps resistive load and the ambient temperature is high, you may need to use a larger conductor than you would in a cooler environment. It is also important to consider the voltage drop in conductors. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. To minimize voltage drop, you can use larger conductors or shorten the length of the circuit. Furthermore, when working with three-phase systems, it is essential to ensure that the load is balanced across all three phases. An unbalanced load can cause excessive current in one or more phases, leading to overheating and potential equipment damage. To balance the load, you should distribute the resistive loads as evenly as possible across the three phases. For example, if you have a total resistive load of 30 amps, you should aim to have approximately 10 amps on each phase. In addition to these practical considerations, it is also important to understand the theoretical underpinnings of single-phase and three-phase power. Single-phase power is characterized by a single alternating current waveform that varies sinusoidally with time. The voltage and current reach their peak values at the same time, and the power delivered to the load also varies sinusoidally with time. In contrast, three-phase power consists of three alternating current waveforms that are 120 electrical degrees apart. This means that the voltage and current in each phase reach their peak values at different times. As a result, the instantaneous power delivered to the load is more constant than in a single-phase system, which leads to smoother motor operation and better efficiency. Moreover, three-phase power allows for higher power densities than single-phase power, which is why it is commonly used in commercial and industrial applications. By understanding these theoretical concepts and practical considerations, you can effectively and safely work with single-phase and three-phase power systems, particularly when dealing with resistive loads. Always consult the NEC and other applicable codes and standards to ensure that your installations comply with all relevant requirements. Always prioritize safety when working with electricity. De-energize circuits before working on them, use appropriate personal protective equipment, and follow safe work practices. Electrical work can be dangerous, and it is important to be properly trained and qualified before attempting any electrical tasks. So, keep in mind that for resistive loads, voltage is directly proportional to the power consumed. If the voltage is the same, the consumption should also be the same.